Now we go into the understanding of module 4, and the contents of module 4 are as follows. So here we will look into sequential circuit design and dynamic logic circuits. In the earlier topic, that is module 3, we had a discussion on combinational circuit design. Right now we are considering the sequential circuit design, which is based on one input following the one input giving us the output, and that output is fed as input to the next circuit. So the basic topics involved in sequential circuit design is it requires memory, and the circuit design, it is the important concept used here are the latches and the flip-flops. And next you have dynamic logic circuits. So this is almost the same as your CMOS, but then extended version of CMOS here with the influence of the capacitor being introduced here. So that is what we will be discussing here in the next topic. Right now our focus would be on sequential circuit design, which is introduction, circuit design for latches and flip-flops. Next topic we have is resettable latches and flip-flops. So it is possible to reset the latch and the flip-flop. So most practical sequencing elements require a reset signal to enter a known initial state on startup and ensure deterministic behavior. So anytime whenever you are using the sequencing and before freshly sending the content, you need to reset the signal. Therefore, when you reset, it is the initial state, and that is the startup procedure, and then whatever you get is based on the signal or based on the data's behavior, and that is called as deterministic behavior. So we have the diagram in the next slide, which shows latches and flip-flops with reset pins. So the purpose of having the reset pins is to freshly start the operation and initiate the actions. Therefore, reset is very much essential. And how is the possibility of reset done? There are two types of resets. One is called as the synchronous and the asynchronous. So what exactly you mean by asynchronous reset and synchronous reset? First we'll talk on asynchronous reset. This forces Q to Q low immediately, while synchronous reset waits for the clock. So in asynchronous, it has no control of clock, and whatever the output you get, immediately it will be reset, whereas in synchronous it waits for the clock until and unless the clock pulse is activated. The reset signal is not high. Reset signal is not waiting for clock pulse in asynchronous type. Immediately it will become Q low. It will force the value of Q to low. Next, synchronous reset signals must be stable for a setup and hold time around the clock edge. So synchronous here, while synchronous waits for the clock, synchronous reset signals must be stable for a setup and hold time around the clock edge. So based on this, therefore they should have a proper setup and hold time, whereas asynchronous reset is characterized by a propagational delay from reset to output. Whereas when it is in terms of asynchronous reset, it has a propagation delay, and that is from reset to the output. So whenever you have been asked for the difference between synchronous reset and asynchronous reset, these are the few differences which you have to quote, and if necessarily you can show it with a diagram, and that may fetch you full marks. Synchronous reset simply requires ANDing the input D with reset. So if you have an input and it is signified and it is equal to a variable D, then a merely ANDing operation. So though I can't call it as multiplication, the logical ANDing operation is performed between the input and the reset. Whereas in asynchronous reset, it requires gating both the data and the feedback to force the reset. So not only a merely product of the input and the reset, it is requirement of an asynchronous reset is it should have both the data and the feedback, and that with the feedback will further force the reset input independent of the clock. Next we have tri-state NAND gate can be constructed from a NAND gate in series with a clocked transmission gate. So here we are talking only about reset latches, and the different types of resets are considered here as synchronous and asynchronous. So these are the representations of resettable latches and flip-flops. So the symbolic structure of a latch is like this, where it has one clock signal, one input and one output with a reset pin. And this is one more version of a flip-flop, which is with D and Q and reset pin and 5. And these are the various diagrams. So two types of resets are there. One is synchronous and asynchronous. So synchronous here is given as reset bar, and these are the representations, and equivalent versions with little more variety and inclusions of different gates is the synchronous reset. Similarly, we have the asynchronous reset here. So these are the representation of resettable latches and flip-flops. So settable latches and flip-flops force the output high instead of low. So always you will have Q here. Output is always forced as high instead of low. They are similar to resettable elements of figure, but they replace NAND with NOR and reset with set. So the reset signal is replaced with set signal, and wherever you had NAND signals, that it is replaced with a NOR gate. Wherever you had a NAND gate, it is replaced with a NOR, and reset is replaced with a set. So this is how we have settable latches. So this figure shows a flip-flop combining both asynchronous set and reset. So you have reset as well as set. Next topic is dynamic logic circuits. So what exactly is dynamic logic circuits? What is it we are going to focus? Introduction, basic principles of pass transistor circuits, synchronous dynamic circuit techniques, dynamic CMOS circuit techniques. So these are taken from the first text, that is Sung Mo Kang, and it is especially with the 9th chapter, and these are the different articles. So we will be focusing on dynamic logic circuit. So we need to understand what you mean by a dynamic logic circuit. So the introduction goes on. A wide range of static, combinational and sequential logic circuits were introduced in the previous chapters. So earlier we had combinational and sequential, and static logic circuits allow versatile implementation of logic functions based on static or steady state behavior of simple NMOS or CMOS structures. So what exactly you have static logic gates are? They are based on steady state, constant state behavior of simple NMOS or CMOS structures. In other words, all valid output signals in static gates are associated with steady state operating points in the circuit. That means in static logic, there is a steady state operating point of the circuit. Therefore, a typical static logic gate generates its output corresponding to the applied input voltage after a certain time delay, and it can preserve its output level as long as the power supply is provided. So in a static logic gate, it generates its output corresponding to the applied, how the output is based on the amount corresponding applied input voltage, and based on that, after certain delay, it is possible to get a output. So that is the reason it can preserve its output level as long as the power supply is provided. So that is the reason for getting a static output or a constant output which is maintained as long as the power is on, because it is after certain delay you are getting the output. This approach, however, may require a large number of transistors to implement a function and may cause a considerable time delay. So we have told, in order to achieve stability in the output, there is a delay encountered, but when you have large number of transistors, and more delay can be piled up, and together we will have a considerable delay. So though the output is static and stable, the delay concerned with the static device is more, and that is what is the concept which is slightly shifting towards dynamic, which has a faster approach. So in high density, when you have more number of ICs, high performance digital implementations where reduction of circuit delay. So when you have a high performance implementation, and when you say it is a high performance, when it has lesser delay and the area, lesser area. So then we call it as high performance. In that case, it is the dynamic logic circuits which offer significant advantages over static logic circuits. So that is where we get more advantages. Therefore, the operation of all dynamic logic gates depends on temporary storage of charge. Therefore, how though it is advantageous than the static, how exactly it operates. So the operation of the dynamic logic gate depends on temporary storage of charge. So you have a capacitor there and it is storing the information for a short interval of time, and it is happening in the parasitic node capacitance. So normally it is at the diffusion, this capacitance is placed and there it is storing the information instead of relying on steady state circuit behavior. So dynamic logic gates information is stored on a charge which is at the parasitic node capacitance. This operational property necessitates periodic updating of internal node voltages. Because of this, it is very much necessary to update internal node voltages, since stored charge in a capacitor cannot be retained indefinitely. So capacitor will retain its charge to little amount of time. The moment it capacitor also has a feature that it will gradually decay its output, it will discharge. So till the amount of till the time it is storing the information, we need to have that measure in terms of internal node voltages. Therefore, consequently, dynamic logic circuits require periodic clock pulses in order to control charge refreshing. So, by helping the refreshing of the charge, it is very much essential with the help of a clock circuit. So, clock signals helps us to control charge refreshing. Whenever you don't want the information to be stored, you can refresh it, you can clean it. So that happens at the interval, at the moment when the clock signal is given. The capability of temporarily storing a state, that is a voltage level at a capacitive node, allows us to implement very simple sequential circuits with memory functions. So we have to understand here, whenever you have a temporary storing place, that is a voltage level, or in other words it is the capacitive node which will help us to have the information stored, then in that case we can consider it as a sequential circuit. So because it is storing for certain interval of time, it can go to the next circuit after certain interval of time, sequential, and therefore the component called as memory comes into picture, which stores the information. Also, the use of common clock signals throughout the system enables us to synchronize the operations of various circuit blocks. And if you are using a common clock, you will have a synchronized data. So, if you are using a common clock, at a time you can control 4 different gates. If you have 4-bit, you have to control 4 different gates. So, at a time you can control means it is storing the data and refreshing the data at a time. So this is called as synchronizing the operation. At a time it happens. As a result, dynamic circuit techniques lend themselves well to synchronous logic design. Therefore, it is helpful, dynamic circuit is helpful in synchronous logic design. Finally, the dynamic logic implementation of complex functions generally requires a smaller silicon area than does the static logic implementation. So we have to understand a little more bit about the dynamic logic implementation if it is with the respective to complex functions. So whenever we have complex functions, it requires smaller silicon area than that of the static. So that is one of the added feature or the advantage of dynamic logic. As for the power consumption, Okay, next in terms of area dynamic logic reduces or consumes lesser area. Next in terms of power consumption, which increases the parasitic capacitance, the dynamic circuit implementation in a smaller area will consume less power. So obviously when you have lesser area, definitely it consumes less power despite you have the clock signals. So this is one of the another feature of dynamic logic. It consumes lesser space or lesser area, and as a result it also consumes lesser power.